Hi everyone. Today I'm going to discuss the derivation of the double integration method. Though there are four basic deflection methods, namely the double integration method which will give the acronym DIN, the area moment methods or the area moment theorems, which we will give the acronym AMN, and third we have the slope deflection or the conjugate beam method, which we give the acronym CDM. And lastly, we have the energy method, which has two sub-methods, namely the virtual work method and the Castigliano's second theorem. So our main concern in this video is the derivation of the double integration method. So let's consider a beam that is loaded with an arbitrary loading to generalize the derivation of the double integration equation. So with this loading, it will deflect and the elastic curve will be this one, and this is highly exaggerated because the actual beam you cannot see it that it will bend that way. So it will appear with our naked eyes as straight, but this is for the purpose of derivation. So let's consider 2 points in the elastic curve C and D, and furthermore, we consider a very small element of this elastic curve which is circled here, and we magnify that into this form so that this is the portion of the elastic curve which is very small, and this is the beam. So we have here the radius of curvature, they meet at that point there. So again, this is highly exaggerated or distorted figure. But in fact, this differential S here is almost straight in reality. So the radius of curvature is denoted by R, and the central angle denoted by, because this is very small, differential theta. The arc length therefore is equal to the differential S, and actually this differential S is almost equal to differential X, because as I said, the curve, the elastic curve is almost a straight line. So this is just for the sake of uh, magnification so that you can imagine. So this straight line distance is actually almost equal to the dx, as I said. So since from geometry, the arc length is equal to the product of the radius of curvature and the central angle, d theta, and I hope you know that from S equals r theta from geometry or from trigonometry, then because the deflected shape is highly distorted, that actually ds is equal to dx practically, and the slope theta is very, very close to 0. So that ds is equal to dx, and dx is equal to, from this equation, r d theta. So then we draw a line parallel to this radius here so that the angle formed between these two lines is the same as the theta. So this arc length therefore is equal to ds, and this is the uh, deflection, or this is the change in length of ds. So if we denote the radius of curvature here from the neutral axis as y, and because the angle is d theta, also d theta, so imagine that y is the radius, so this deflected part, or this elongation of ds, is y d theta, just like arc length is radius times central angle, so this is radius y times d theta. From strength of materials, he learned that normal stress, or sigma, is equal to my over I from flexure definition, and this is equal to proportional to strain, and the constant of proportionality is the modulus of elasticity. So stress is proportional to strain, or stress is equal to modulus of elasticity times strain. Then this strain here is equal to this deformation yd theta divided by the original length, which is ds. So sigma, which is equal to my over I, is also equal to strain, which is yd theta divided by ds. So because ds is practically equal to dx, because the fact that this elastic curve is really almost a straight line, so m over ei from this equation here is equal to d theta dx, and from here m over ei, we cancel out y, is equal to d theta ds, and ds is replaced by dx because they are practically equal, and therefore it is equal to 1 over r, because from here d theta ds, replace ds by dx, is 1 over r. So it is the reciprocal, m over ei is the reciprocal of the radius of curvature. So from here, we have tangent of theta equals dy dx. The slope of the tangent to the elastic curve is, from calculus, derivative of y with respect to x. And because the angle is very small, tangent of theta is practically equal to theta itself when converted to radians. So you may try there. 1 degree. 1 degree is a considerable angle that cannot be considered a small angle. You may try zero point 0.5, that's considered small, 0.5 of a degree. So you press tangent of 0.5, then convert 0.5 degrees to radians by multiplying 0.5 by pi over 180. You will see there that tangent of 0.5 degree in decimal will be practically equal to 0.5 degree times pi over 180 to convert it to radians. So that's it, because as mentioned a while ago, the elastic curve is actually almost a straight line, almost horizontal. That the slope of the horizontal line is practically almost zero also. So theta, which is dy dx, is equal to y prime, the other expression for dy dx. So remember that for very small angles, such as the slopes in beams and frames, tangent theta is practically equal to theta itself when converted to radians. So d theta dx from this expression here is equal to the derivative of theta. Theta is equal to dy dx, because the angle is very small. Then that becomes derivative of theta with respect to x is the second derivative of y with respect to x. Since d theta dx is m over ei from this equation here, then m over ei is equal to the second derivative of y with respect to x, or simply ei, second derivative of y with respect to x, or ei y double prime equals moment. And I hope you already familiar with this differential equation of this elastic curve. So this is the differential equation of the elastic curve. So it is a second degree differential equation. So, sorry, second order differential equation. So this is the differential equation of the elastic curve of the beam. So I think you're familiar with this. Ei y double prime is simply equal to the moment at any point on the section of the beam. So integrating once, so we have ei dy dx equals ei y prime equals integral of m dx. So after we integrate this expression, or we break this into dy dx, then this is m dx, and integrate. So ei dy dx, which is ei y prime, equals the integral from x1 to x sub 2 So any point, it may be that is from C to D. X sub 1 would be distance from A to C, then X sub 2 will be A to D. Then integrating further, so by the way, this represents the slope of the tangent to the curve. Integrate ei dy dx is equal to eiy prime, or integral from x1 to x2 of m dx plus c sub 1. Now, c sub 1 is interpreted as the slope of the tangent at the origin. So it may be point A as the origin. Then if the left support is a pin or a ruler, then there will be slope at that origin. If point A is fixed, then the slope of the tangent to the fixed support is horizontal, so it is 0. So therefore, that will only be 0. So integrating further, so that's the slope of the tangent to any point to the elastic curve. Integrating further, so we have eiy prime equals ei delta, or the deflection. We have double integral of m dx plus c sub 1 dx. So that's it. So this represents the equation of the elastic curve. This one is the differential equation of the elastic curve, and this is the solution. So we have here the equation of the elastic curve. So therefore, y represents the deflection from the horizontal x-axis. So if it is negative, then it is below. If it is positive, then it is above the x-axis. That's the meaning of that. Then from before, so this is the equation of the elastic curve. And by integrating that equation before, then we have double integral of m dx dx plus c sub 1x plus c sub 2. C sub 1 is the slope at the origin, as I said, and c sub 2 is the deflection at the origin. So if the origin is a support, then c sub 2 will be 0, but there is value of c sub 1. When the support is fixed, then there will be no c sub 2 because there is no deflection at the fixed support, and there is also no initial slope at the fixed support. So this is the equation of the elastic curve. So in the above equation, c sub 1 is the slope of the tangent at the origin, while c sub 2 is the deflection at the origin. So if the origin is a perfectly fixed end supports, then both c sub 1 and c sub 2 will be 0. If the origin is a support, maybe ruler or pin, then c sub 2 will be the only 0 term, regardless of whether that origin supports or settles. So that's the theory. And don't forget to subscribe in my YouTube channel so that you will be updated with my lecture videos, especially in the subject theory of structures. Thank you for watching.